And do you have any questions? So one thing maybe I can add is that here is this both y1 and z1 are elements of y union z, right? So the problem here is that so y1 is in y union z and z1 is y union z. But as you saw over here, y1 plus z1 was not in that union. So at the beginning of the course, these concepts might be confusing. So please try to get yourself comfortable with the union of the sets, the intersection of the sets, the sum of sets, and sum of between vector elements, summation between field elements, etc. So they tend to be confusing at the beginning, but the more we progress, it will be more clear. So let's continue with another important definition. And this is another. So previously we've seen how to build vector spaces by using definitions of field. And here we will try to construct some new vector spaces by using the existing vector space. But the one condition is that they should share the same scalar field. So let me read the definition that I will talk about product space. So let V and W be two linear spaces defined over the same scalar field. Then this is important, so it is worth underlining that. Then you can define the product space of these two vector spaces as follows. So we can combine those vectors. This is the first vector from V and the second vector from W. And you can define the addition operation by the vector addition operation of the corresponding vector spaces. And you can define the scalar multiplication since they are sharing the same scalar field by using the corresponding scalar multiplication operation of the corresponding vector spaces. Okay. And this way you can construct, for example, let's say r square. Okay, so actually this r square vectors, and this is the field here, okay, is the product space of r and r. Okay, so maybe I should specify once again. So this is the field, okay, of the vector space. This is the field of the vector space because one of your friends asked at the beginning of the lecture, and this is the, let's say, vector space V, and this is the vector space W. And so they share the same scalar field R, and the resulting product space also shares the same field. Okay. The associated field with the product space is the same, and that is, in this case, the product space, W. Okay, so this is how we go to R square, Rn, etc. From vector spaces. Okay. And another important definitions are coming. One of them is the linear combination of vectors. So the linear combination of n vectors of a linear space C is the vector of the form a1, x1, a2, x2, an, xn, where ai's are all scalars in F. So a linear combination is just you multiply all of these vectors with a scalar from the field, and you add up the sum up the resulting vectors. And the set of all linear combinations of x1, x2, xn, these n vectors, is called span of these vectors, and it is denoted by sp x1, x2, xn. Sometimes we use with the capital letters, the s is capitalized here, sp. Okay, so these definitions will be more important when we will talk about basis of vector spaces, basis sets. Also, you're already familiar with all of these definitions, I'm sure. And another important definition is the linear independence. So the n vectors in X are said to be linearly independent if and only if a linear combination of these vectors being equal to the zero vector of the vector space implies that all the coefficients in that, all scalar coefficients in this linear combination themselves are equal to zero. Okay, so if you find non-zero coefficients, this one of them, two of them being non-zero, means that these vectors are linearly dependent. Maybe there's another definition of linearly independence that you are familiar with from the undergraduate courses. What is that? So as you may remember, so if you can express one of these vectors in terms of the others as a linear combination, then this means that these set of vectors are linearly dependent, right? And the reason is that I can then write down the coefficients which are non-zero, add them up, and get the zero vector of the vector space. Okay, so let's see some trivial examples then. So let's say, let's get those two vectors. 0. So this is a linearly independent set. And what is span of x1 and x2? It is r square. Okay. So we can write any vector as a linear combination of x1 and x2, right? Let's say if this is a point, this 8 times 1 0 plus say b times 0 1, right? Okay, let's consider some other examples. So let's consider 0 1 and 1 1. This is x1 again. This is x3. So this is again a linearly independent set, and span of x1 and x3 is again r square. I mean, if you can you can get the endpoint AB this time. AB by using the vectors x1 and x3, right? So it will be something like that. So this is this is a times x3, and that component is b minus a times x1, right? So that you will end up with a and b over here. So another example, let's go to 3 dimensions. So 1, 2, 3, 4, 5, 6, and 7, 8, 9. V1, V2, and V3. So is the set linearly dependent or independent?
Independent.
So it is. It looks like an independent set, but so what is the independence condition? A linear combination being equal to 0 should imply that all the scalar coefficients are equal to 0, right? So if I can find the linear combination of these 3 vectors, which ends up being equal to 0, where the scalar factors are not equal to 0, at least one of them, then I can conclude that these vectors are linearly dependent. Okay. And for these true vectors, if you just look at 2 times v1 minus 4 times v2 plus 2 times v3, that is equal to 0 actually. So therefore, this is not linearly independent. So because I was able to find non-zero coefficients here, not linearly independent. All right, so one should be careful when claiming about dependence and independence. So you should consider all possible linear combinations and show that all of these coefficients are equal to 0 if a linear combination is equal to 0. If I find even one counterexample, then the linear independence drops. So let's also consider, we said that these vector spaces are also defined over the polynomials with degrees less than a certain number, right? So let's consider the linear space of polynomials with degree less than or equal to 2. And let's define a subset P1, P3 such that P1 of t is equal to 1, P2 of 2 is equal to t, P3 of t is equal to t square. Okay, so these are the 3 vectors in our vector space. Okay? So it is the function space. These are real valued functions. They are real valued functions. T is a real number. Okay, and what we'd like to investigate is the sets P1, P2, P3 a linearly independent set or not. Okay. So the way we will do it is that we will simply apply the definition. Okay, so to check if this is a linearly independent set or not. So write as, let's apply the definition. So definition says that a linear combination of those guys being equal to 0 should imply that all scalar coefficients are equal to 0. Okay. So A1 P1 plus A2 P2 plus A3 P3 being equal to 0 should imply that all A1, A2, A3 are equal to 0. Okay. So I would like to emphasize one thing, that so this is the zero vector of the vector space, right? So this is 0 V. This is actually the zero polynomial. So it is the function, so we're in the function space, that takes the value 0 for all values of t. That is the zero polynomial. Okay. So let me write it down also this more explicitly as a1 of p1 of t plus, oops, sorry about that, a2 of p2 of t plus a3 of p3 of t should be equal to zero polynomial. So this is zero polynomial of t for all t. Okay. So in other words, so if I write down this the vector elements themselves here instead of p1, so a1 plus a2 times t plus a3 times t square should be equal to 0t squared plus 0t plus 0, okay? I mean, this should be equal to 0, so this being equal to 0 should imply that all coefficients are equal to 0 for all t, okay? And this is 0 if only these coefficients are all equal to 0. So we'll say that a1 is equal to a2 is equal to a3 is equal to 0. And therefore p1, p2, and p3 are linearly independent. And another example can be, for example, p1 of t is equal to 1, p2 of t is equal to 1 plus t, and p3 of t is equal to, let's say, 1 plus t square. Okay, and let's say the set S is equal to p1, p2, and p3. So the question is the set linearly independent? Any initial guesses? In the meantime, I can write down the condition. So that should be 0 if and only if a1, a2, and a3 is equal to 0. Okay. So any initial guesses about the linear independence or dependence of this set?
Linear independent hocam.
That's correct. That's correct. So let's replace these p1s with their definitions over here. So we're talking about a1 plus a2 plus a2t and a3 plus a3t plus a3t square. Okay, we're talking about that being equal to the zero vector. The zero vector space is 0t squared plus 0t plus 0. And this is only satisfied, so let me group the higher order terms first. a3 times t squared plus a3 plus a2 times t plus a1 plus a2 plus a3 is equal to 0t squared plus t plus 0 for all t. And as you see over here, for this thing to be equal, a3 must be equal to 0. And if a3 is equal to 0, then a2 must be equal to 0. And if a3 and a2 are equal to 0, then a1 plus a2 plus a3 should be equal to 0, and a1 should be equal to 0. So this is almost satisfied when all of these coefficients are equal to 0. And I can conclude that this is linearly independent set. Throughout
Hocam.
this course, buyurun lütfen.
Hocam mesela örneğin sınavda böyle bir soru sorsunuz ya da quizde. Ben bunu Wronski'nin determinantından kanıtlasam, göstersem kabul edersiniz değil mi?
Tartışma çıkar aramızda. Şey nedir o? Öncelikle şey göstermek isteriz hani örneğin bazı sorularda sadece işte axiom of the field'i kullanaraktan ya da sadece işte şey nedir o? Field definition'ı kullanaraktan gibi şeyler söyleyebiliriz yani. Ama öyle şeyler belirtmediğimiz takdirde farklı yollardan gösterirseniz sorusuna bağlı olarak hani size aksi şeyler iddia edilmediği sürece makul olabilir yani.
Anladım hocam. Yani çünkü 219 dersinde mesela 2 tane solution buluyorduk. Bunların linear independent olup olmadığını göstermek için mutlaka şey yapmamız gerekiyordu. Onun determinantının atıyorum sıfırdan farklı olduğunu göstermemiz gerekiyordu.
Yani şey dersek işte hani biz by using the isim definition derseniz hani bu yolla yapmanız gerekir yani. Anlatabildim mi?
Anladım hocam.
Hani
Tamam.
by using the definition of the linear independence dersek bu şekilde yapmamız gerekir yani. Ama hani diğer yolları da bilmek her zaman önemli. Ya burada ben bir şeyin altını çizmek istiyorum. Arkadaşlar bu grad dersi ya. Hani sizin bir yolu farklı yolla çözebilmeniz, işte şeyleri başka bir şeye fazladan teoremler bilmeniz, başka şeyleri yapabiliyor olmanız ziyan olan bir şey değil. Hani hatta bu ders kapsamında özellikle bu işin ABC'si öğrenirken sadece bu ders kontentiyle, sadece bu sınıfta konuştuklarımızla da bağlı kalmamak lazım, sınırlı kalmamak lazım. Hani dolayısıyla yüksek lisans çalışmanızı yaparken alet çantanıza ne kadar tool eklerseniz o kadar avantaj sizin için. Hani oradaki hani midterm'de o soruda bir spesifik olarak definition'ı kullanmamış demişiz aslında çok detay hiç de önemli olmayan bir durum olmuş oluyor. Önemli olan sizin yüksek lisans çalışmanızı yürütürken işte gerekli teorik altyapıyı kendiniz build up etmeniz çok daha kritik yani. Tamam. Hakkınızda bunu ara ara vurgulamakta fayda var. Çünkü bazen hani undergrad'daki gibi değil yani yüksek lisans derslerindeki yaklaşımlar. Her zaman daha fazlasını kendiniz hani sizi hani sınavda ihtiyacınız olmasa bile öğrenseniz research'ünüzde mutlaka bir gün kullanırsınız yani. Hani ziyan olmayacaktır o bilgi. Anlatabildim mi? O yüzden hani sadece bu dersin kontentiyle değil fazlasına da gitmekte farklı referans kitaplarını karıştırmakta her zaman fayda var. All right, so let's consider another example. So again, we are in the function space and we are given three functions: cos t, sin t, and cosine t minus pi over 3. And we would like to investigate if these guys, this set is linearly independent or not. And the thing is that the answer is no, and the reason is simply this. We can express cos t minus pi over 3 as, what is that, cos t cos pi over 3 plus sin t sine pi over 3 So that is equal to 1 over 2 cosine t plus square root 3 over 2 sine of t. So if I just consider, let's say, for instance, consider minus 1 over 2 cosine t minus square root of 3 over 2 sine t plus 1 times cosine t minus pi over 3, I will end up the zero vector of the vector space, 0 of t, 0 function. But I do have a1, a2, and a3. At least one of them is different than 0. Therefore, this is, in this case, all of them, 2 of them are non-zero. This is a linearly dependent set. Do you have any questions?
Hocam ders sonuna saklıyorum ama şimdi sorayım mı?
Sonda soralım. İyi olur ya. Olur mu?
Tamam.
Şey. bir yandan da merak ettim. Neyse devam edelim bakalım, sonra ders sonunda dinleyelim. So we will continue with very important definition. So the next definition is a definition for the basis set. So let V be a linear space and finite, and we are given a finite set of vectors S, x1 to xn, which is a subset of V, and S is said to be a basis for that vector space V if and only if the span of these vectors is equal to the vector space V itself, and S is a linearly independent set. So this is the definition of the basis set. Okay, so the span should be equal to V and the elements should be linearly independent. And furthermore, this one same vector space can have many different basis sets. Okay, but these basis sets can include different vectors. They can be different sets themselves, but they share one thing in common, and that is all these basis sets must have the same number of elements. Okay, so it has the same number of vectors, so that to constitute a basis for the vector space, and that number is called the dimension of the vector space V. Okay, so the dimension of a vector space is defined by the number of vectors in one of its basis set. And all right, so let's again consider those two bases. But this one we already investigated. So this is a basis set for R square, okay, which we considered already. So I can write down span of S1 is equal to R square, and S1 is linearly independent. So therefore, S1 is the basis for R square. And once again, for S2, I can claim that span of, maybe I can write down here, span of S2 is again R square, I can write any vector as a linear combination of these two vectors over here. And S2 is a linearly independent set. Therefore, S2 is a basis for R square as well.
Hocam bir şey sorabilir miyim?
Lütfen buyurun.
Hocam bu basis değiştirmenin bir avantajı var mı? Yani bir örneğin vektör space'i farklı bir basis'le expand etmenin application açısından bize katkısı oluyor mu? Problemlerimizi
Exactly.
çözmekte.
Exactly, there are many advantages. So we will come to that later. So there will be like a coordinate transformation, and you will in certain applications you definitely would like to express your vector in terms of a specific basis sets. For example, different basis sets can have different properties, right? And for example, this S1 set is called the canonical basis set. And so here you have one element be non-zero, all other elements are equal to 0. And for the second vector over here, one element is non-zero, all other elements are equal to 0. So that's called the canonical basis set. And furthermore, for example, that S1 basis set, these basis vectors are, you will see later on, they are orthogonal to each other. Okay, we will see the definition for orthogonality later on. So in many applications, you may deliberately want to change the basis for your vector representation, and that will play a crucial role in many applications and problems. You're right.
Teşekkürler hocam.
Hocam,
Yes, please.
ben de şey soracaktım da burada mesela S1'in hani şey olduğu oldukça açık hani basis hep kullanıyoruz ama mesela S2'yi tam yani göremedim ben. Ama şuradan şey yapabilir miyiz? Dimension'ını biliyorsak 2 dimension'lı ve 2 tane herhangi linearly independent vektör aldığımız zaman bunlar her türlü basis'tır diyebilir miyiz?
You can claim that, but you have to prove that actually. So there is a proof for that. So it is possible to prove that any this linearly independent in the Rn dimensional space, when we're talking about Rn, for example, and you have n linearly independent vectors, then you can claim that this is a basis set. But there's a proof for that. Okay. Which is not short enough that I can explain here, but you can find it in the resources, in the reference books as well.
Ya o zaman bu S2'nin basis olduğunu görememek, direkt yani daha doğrusu R kareyi span ettiğini görememek normal mi? Prove etmek gerekiyor.
I think you can still show that, right? So if you are given like any vector in the form of AB, you can find the coefficients, right? So what is the coefficient of this thing so that I will end up with the AB point. So you can solve these equations, right? So let's say this is, let's say B1 and B2. So if you're given any point like AB and you need to show that alpha 1 times B1 plus alpha 2 plus B2 is equal to the points AB. So then you have two equations, two unknowns. This is given, then you can find the coefficients, right? So you can show that all these coefficients. So it shouldn't be very difficult. But the one thing that you emphasized was important in the sense that yes, you're right. Any two linear independent vectors in this R square constitute a basis. I mean, but if, for example, if in the exam you would like to use that fact in your proofs, then you need to prove that as well. Okay. So you can, it's in the reference book, for example, you can find that in our first reference book. Okay. If it is, you can also come and ask me anytime. So let's consider another example. Say S3 is composed of those vectors 1, 1, 1, 0, and 1, -1. And the question is, can S3 be a basis for R square? And definitely not, because of the fact that S3 is not a linearly independent set. And furthermore, number of elements in S3 is not equal to dimension of R square, which is equal to 2. All right. So I would like to emphasize one thing. So in this course, you are usually given many definitions, like the next definition that will be about an ordered basis, okay? So in this course, throughout this course, especially at the beginning, you will be given many definitions. I'm sure you understand the definitions, but at the beginning you don't know what we are going to do with those definitions. So why we are getting those definitions, what to do with them. So, and this might be a little bit confusing at the beginning of the course. But good news is that I can assure you that as we progress throughout the course, it will be more and more evident why we are learning those definitions. So why we needed these basis definitions, why then we need these ordered bases, etc. So for example, here we will talk about first a basis set, and then we will talk about an ordered basis such that these vectors in the basis set are given a specific order. And if the basis sets are vectors are given a specific order, then I will be able to talk about the coordinates of these points. So coordinates of a given vector in terms of a given basis set. Okay, so that we can talk about the coordinates. Then I can talk about this coordinate transformation, which is related with another question that your friend asked a while ago, changing the basis, etc. So we will build up all of these things in time, and it will be more evident why we are learning this. But at the beginning, there might be like too many definitions coming without sufficient motivation, right? So why did we learn that? Why? So maybe at this stage you might need to be patient and motivate yourself, and later it will be more evident why we're learning all these new concepts. Okay. Okay, so in my explanation I already gave a definition. The next definition is the ordered basis. So it's a basis where the base vectors are given a specific ordering, and if x1 xn is an ordered basis of V, and if we are given any vector in our vector space V, then there is a unique n tuple of scalars, like there are unique n scalars such that Y is expressed as a linear combination of these ordered bases where the coefficients are coming from these n tuple A1 to AN. So scalars A1 to AN are called the components of Y with respect to the ordered bases x1 and xn. And the next definition comes with the coordinates of V, okay? And let's have a look at the definition. So given n-dimensional linear space V over a field R, And given a basis set B, which is composed of n vectors over here, and this is an ordered basis for this vector space. And if a vector in our vector space satisfies that, can be expressed as a linear combination of these basis vectors, where all of these coefficients are real numbers, then these coefficients alpha i's are called the coordinates of the vector v with respect to basis b. Okay, and we use this definition. So if I can write v as a linear combination of these basis sets alpha I, vi, and if I put all these alpha 1, alpha 2, alpha n into another vector itself, this will be, notice that this is another n tuple, let's say. Okay, that notation implies that gives us the coordinates of the v vector with respect to basis b over here. And we use the notation. So if alpha is defined as follows, we use the notation alpha is the representation of v with respect to basis b. Okay, I think it will be easier if we see some examples. All right, so let's R2 by 2 denote the linear space of real valued 2 by 2 matrices. And the addition and scalar multiplication are defined element-wise. I mean, if you're adding two elements of the vector, which means if you're adding two 2 by 2 matrices, the addition operation between those two vectors, so this is vector 1, this is vector 2, is defined by element-wise addition of their elements, okay? And the scalar multiplication is again done with this is a scalar in R, and it's a 2 by 2 matrix, and it is defined by the element-wise multiplication. Okay. And if we are given a basis set, let's say B is equal to, let's say 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So notice that this is a canonical basis. Let's say here's all right. Okay. So if we are given a matrix M, which is among these 2 by 2 real matrices, so it's in the form of elements which are real numbers here, A, B, C, D. So since this is a vector in my vector space, which is a the vector space of 2 by 2 matrices, and if this is a basis set, I should be able to write that vector as a linear combination of these guys. And here it is a bit straightforward. This is equal to A times 1 0 0 0 plus B times 0 1 0 0 and plus C times 0 0 1 0 and plus D times 0 0 0 1. Then the coordinates of M with respect to basis B, so coordinates of M with respect to basis B is the n tuple, which is composed of these scalar coefficients like A, B, C, D. Okay. So notice that the vector space was like a 2 by 2 matrices, but the coordinates are n tuples, like this 4 coefficients combined together. And similarly, we can extend this definition to in the function space. So let's consider again the linear space of polynomials with degree less than or equal to 2. And let's define a basis on this vector space P1, P2, P3 such that we have P1 is equal to 1, P2 is equal to T, and P3 is equal to T squared. And if we are given any vector in our vector space P, which is in B, then P of T can be expressed as, since it's a polynomial with degree less than 2, as A plus BT plus CT squared. And the representation of P vector with respect to basis B, which is over here, is equal to this n tuple, like these three coefficients written down together, A, B, and C. So I think it's important to emphasize that we said we can define the coordinates of the vectors with respect to some bases, and maybe you can already see some advantages of doing that, right? Because of the fact that now here our vector space was 2 by 2 matrices, okay, and if I wanted to represent a given matrix, I was able to write down their some coordinates, these and 4 tuples. And for example, I can do some algebraic manipulations over these coordinates instead of M itself. Okay, and again here we have a vector space of polynomials. These are the function space. These are continuous functions and polynomials. And again, instead of making some manipulations directly on the polynomials, for example, for the linear transformations, etc., towards the next lectures, we will see those. We will be able to do manipulations on their coordinates, which are given with respect to certain bases. So these two will be equivalent at a certain stage. So we will see that later in our course. So that will be some advantages. Okay, and then let's consider another example. So in our next example, it is said that we are given an ordered basis B1, which is composed of x1 and x2 over here in R square. And let the vectors y1, y2, and y3 be presented as follows. So the representation of y1 with respect to basis b1 is equal to 1, 1. Okay. Then representation of y2 with respect to b1 is equal to 1, 0. All right. And representation of y3 with respect to b1 is equal to 2, 3. So we can simply then say that, so if the representation of y1 with respect to b1 is equal to 1, 1, then y1 is equal to 1 times x1 and 1 times x2. This is it. And if the representation of y2 is equal to, with respect to basis b1 is equal to 1, 0, then I can simply say that y2 is equal to x1, right? Plus 0 times x0, so y2 is equal to x1. And y3 is equal to 2x1 plus 3x2, because its representation with respect to b1 is equal to 2 and 3 over here. Okay, so if we change a new basis, an ordered basis B2, which is composed of y1 and y2, question is, can you express y3 with respect to this new basis? So if I would like to express y3 with respect to new basis, I should be able to write y3 in terms of y1 and y2, right? So first of all, y1 is equal to x1 plus x2. Maybe I can write that. And y2 is equal to x1, right? And y3 is equal to 2x1 plus 3x2, right? So I should be able to express y3 in terms of y1 and y2. So the good news is that I can change x1 directly with y2 over here, right? So 3 is equal to 2y2 plus 3x2, right? And if I can get rid of this x2 over here and write something in terms of y1 and y2, I can express y3 in terms of y1 and y2. And if you subtract those two equations, I can say that x2 is equal to y1 minus y2, right? Then I can write y3 is equal to 2y2 plus 3 times y1 minus y2. And y3 will be simply equal to 3y1 minus y2, right? Then what the representation of y3 with respect to this new ordered basis B2 will be those coefficients, right? 3 and minus 1. So it will be 3 and minus 1. So do you have any questions?
Hocam burada B2'nin ordered basis olduğunu nereden anladık?
Söylemesi lazım. Hani our new ordered basis. Okay, şöyle. Ya aslında şuradan anladık. Koordinatlardan bahsediyorsak zaten ordered olmak zorunda. Hani ordered değilse koordinatlardan bahsedemeyiz. Another question?
Hocam,
Okay. So,
ben
buyurun.
ordered olmasının tanımını tam olarak anlayamadım. Ne demek ordered olması demek?
Belli bir sırayla verilmiş hani yani şey birincisinden ya şimdi şöyle bir şey. Hani diyelim ki hani r square'da işte r square'da bir şu vektör verilmiş olsun, bir de bu vektör verilmiş olsun. Hani ben koordinatları verildiği zaman hani örneğin 2'ye 3 koordinatlarından hani birinci vektörden 2 tane alacağım, ikinci vektörden de 3 alacağım, gelip de buraya geleceğim biliyorum gibi. Hani ordered olması, biliniyor olması hani sırasının.
Yani belli bir kurallar olmasına gerek yok ama fix olması gerekiyor. Öyle mi?
Evet, aynen öyle. Kesinlikle evet.
Anladım hocam.
Fixed olması sizin tabirinizde doğrudur. Hı hı. Any other questions? So it is fixed so that I can talk about its coordinates, right? If I need to specify the basis for the coordinates, it should be fixed, as you said. Good point. Another question? Okay, so I wasn't aware of the time, so it is already past 6:30. So what I was going to do, this is a short proof, but it's a fun proof. So please try to do it yourself. Maybe we can do it together in our next lecture as well. Okay. So we can continue on our next lecture. So at this stage, I will stop recording. So